Hello, I hope you guys can hear me. Let me just set up some things. Also, last stream I had to go, so that's why I had to suddenly end. I'll continue from where I left off. Was the minimum maxima chapter. I'm just setting up my chart. Okay, let me change to full screen. Okay, so last stream I did linear approximation and differentials. And I started maxima and minima, but I had to leave early. So, continuing from here. Think I read this, but let's just read it again. Right. Okay. Consider the function f of x is equal to x squared plus 1 over the interval minus infinity to infinity. As x goes to infinity, f of x also tends to infinity. Plus infinity and minus infinity. Okay. Therefore, the function does not have a largest value. However, since x squared plus 1 is greater than or equal to 1 for all real numbers of x, and x squared plus 1 is equal to 1 when x is 0, the function has a smallest value, 1, when x is 0. We say that 1 is the absolute minimum of f of x is equal to x squared plus 1. Okay. So let f be a function defined over an interval I, and let C be in I. We say f has an absolute maximum on I at C if f of C is greater than or equal to f of x for all x in I. Okay, the wording is pretty strange. So from what I understand, here's a function and I define an interval. Let's say this. Do this, I guess. And then I is basically all these integers, this entire set. And then C is inside I. So C is somewhere here. We say f has an absolute maximum on I if f of C is greater than or equal to f of x for all x within I. Yeah. So this point over here, let's say C, it's an absolute maximum because f of C is greater than or equal to all values of x, which is between this, just between this. And I can describe something similar for the absolute minimum. So I can do like this. So if this is A, B, this here as is the absolute minimum, since f of c is the smallest value within the interval. Between A and B. Also, if B was not here, if B was over here, then this would be the absolute minimum. We say f has an absolute minimum on I, so let I be this interval, at C if f of c is smaller than or equal to f of x for all x in I. These values are absolute extremum. Okay, extreme value theorem. If f is a continuous function over a closed bounded interval a to b, then there is a point in a b at which f has an absolute maximum, and there is a point at which f has an absolute minimum. Okay. A function f has a local maximum at c if there exists an open interval I containing c such that I is contained in the domain of f and f of c is greater than or equal to f of x for all x within I. Okay, this wording is kind of weird. Local maxima at x is equal to 0 and 2. Local minimum at 1. So an absolute maxima is also a local maxima. Okay, so from what I understand, this is considered a local maxima because you can create an interval around it where this point would be the maximum. This is not considered a local maxima because you cannot create an open interval. By open I mean like this. This would be closed. This would be open. So over here I can make an open interval where c would be the maxima, and over here you cannot create an open interval where this point is the maxima. You can create a closed interval. So if a is on the point, it's like this, or this, then this would be, well, let's see, it's basically like this. This here would be the minimum in a closed interval, but this wouldn't work within open one. Yeah, and for the next one, when there's a local maxima or minima, like this a smooth one, or like this where the derivative are undefined. So the derivative is either 0 or undefined. Then it's a local maxima or minima. Let C be an interior point in the domain of f. We say C is a critical number of f is if the derivative is 0 or the derivative is undefined. We call the point a critical point. If f has a local extremum at point x equals to C, then C must be a critical point of f. This is known as Fermat's theorem. If it's differentiable, then it would be 0. If not, then it would be undefined. Okay, right. Let's take a picture. It says to use a graphing utility. Wait. Can I do it without? Let's do some other one then. Yeah. So let's derive this minus 2x plus 3. Okay. So this graph is like, it's a very steep graph like that. So that means as x is increasing, the derivative keeps on increasing. So it's probably like shape of the graph is like this. So x gets greater and greater and greater. The derivative gets greater and greater. Derivative is higher and higher. Over 1. So let's see when this is 0. And so the lowest point is at 3/2. 1.5. So there is a local minimum here, and that's it, right? So let's do B. Okay, this one is kind of tough. Two x minus 3 and 3 cancels. So 2/3 minus 3/3. This gives you this, and if it's 0, then 2x this and then this, and then x is 1, right? Would it be any other value? Zero into so the derivative at is 0 when x is 1. Is that a minima or a maxima? Uh, so minus 1 also the answer. Oh yeah, that would make sense. So x is equal to 3 over 2. Or if it's in this interval, then the maximum is 3. Also over here, the maximum is 2. No, maximum is f of 3. Over here, the maximum is f of 2. At minus 3 over 2 and add 3. Then the other one at 1 and add 2. Okay. If you're finding an absolute minimum, wait, let me get the answer key out. If you're finding an absolute minimum over an interval a and b, what do you need to check the end? Why do you need to check the endpoints? I mean, the endpoints could be a minimum. That's why. Because if the derivative is 0, because like the derivative may not be 0 within the endpoints, like in between the endpoints. So that's why the one of the endpoints might be a minimum. Should I go to next one? What number is this? 91. What is this? I think it would be better if they gave a few example answers. Never mind. Should I go next? The mean value theorem. The mean value theorem is one of the most important theorems in calculus. We look at some of its implications at the end of this section. First, let's start with the special case of the mean value theorem called Rolle's theorem. Rolle's theorem states that if the outputs of a differentiable function are equal at the endpoints of an interval, there must be an interior point C where the derivative is 0. Okay, that makes sense. Yeah, I guess that checks out. If it's not differentiable. If f is not differentiable, even at a single point, the result may not hold. Okay, what's the main value theorem? Let f be continuous over the closed interval a and b and differentiable over the open interval a to b. Then there exists at least one point C which is in a and b such that the derivative is this. Okay, so what I understand, if it's defined a and b, then you have this slope over here. The rise over on. Let's say this is equal to m. So the mean value theorem is that there is a point C in between such that C is equal to m. Sure. It's like the Rolle's theorem but slanted for all orientations. Okay. Do we really need proof for this? Okay, this is checkpoint. Corollaries of the mean value theorem. Let's now look at three corollaries. How do you pronounce this? At this point, we know the derivative of any constant function is 0. The mean value theorem allows us to conclude that the converse is also true. In particular, if the derivative is 0 for all x in some open interval, then f of x is constant over that interval. Yeah, what do you mean? for all x in some open interval. Let h of x be f of x minus g of x, then the derivative is equal to derivative of f of x minus derivative of g of x, which is 0. By corollary 1, there is a constant c such that h of x is equal to c for all x in an open interval I. I don't get this. If f and g are differentiable over an interval I, and f of the derivative of f and the derivative of g for all x in I, and if the derivative is equal, then f of x is equal to g of x plus c for some constant c. I understand. Let's say you have a function f of x. You have some derivative over here. You have all these gradients. G of x will have all the same gradients, so basically the same shape. If the shape is the same, then f of x is g of x plus c. That is, if the gradients are equal. This implies this. And guess it's biconditional. Increasing and decreasing functions. Yeah, what was the first quality? Oh yeah. The first one says if the derivative is 0, then f of x is the constant. The third one, let f be continuous over the closed interval a to b and differentiable over the open interval a to b. If the derivative of f of x is greater than 0 for all x between a to b, then f is an increasing function over a and b. Okay, if it's less, then it's a decreasing function. All of them make intuitive sense. So between a and between b, these are not straight lines. Never mind. Between a, the derivative is always positive. So let's say the derivative is always positive. So this won't happen. This won't happen. So it's just like this, increasing, or if it's always negative, decreasing. Wouldn't it be? Or the following exercises determine over what intervals, if any, the mean value theorem applies. Isn't it all intervals? One five three and 155. Okay, so not 0. Okay, not where it's undefined. Oh, it has to be differentiable over the interval. Continuous and differentiable. Okay. Or the following exercises determine whether the mean value theorem applies for the function over the given interval. Justify your answer. Between 0 and 1, this is true because it's differentiable. Tan 0 to 2, I guess. No, wait. No, I don't think this is true. True, false. It has to be differentiable. I think this is true. Yeah, between 0 and 3, this is true. It's true, false, true. I don't want to do the rest. Yes. False, yes. Okay. Show that this and this have the same derivative. What can you say about this? I mean, if the derivative is same, then the shape of the graph is the same, right? Wait, let me take a picture. Hold on. Y is equal to, what am I doing? The derivative of this is equal to derivative of cosecant is equal to, I forgot. Hold on. Okay. So for cotangent, it's minus cos x square. For uh, for cosecant, it's minus cotangent cosecant x. And then derivative is this. It's minus um okay, so the derivative cosecant square x to cosecant x, then the derivative of the inside, and then the derivative, wait, hold on, then this is equal to 2 square minus 2 cotangent x. Now the next one, this, and then the derivative of this, which is cosecant cotangent. So basically, just this. So I've proven that the derivative is the same. Now, if I have a triangle and I have x 90, opposite, adjacent. What would cosecant be? This is cotangent. Keep forgetting. So, dua. Show thing show chatao. So cotangent is adjacent. Forget this. Never mind. It's trying to get somewhere. derivatives and the shape of the graph. Earlier in this chapter, we stated that if a function f has a local extremum at a point c, then c must be a critical point of f. The first derivative test. Using function 4.31, we summarize the main result regarding local extrema. If a continuous function f has a local extremum, it must occur at a critical point c. The function has a local extremum at a critical point c if and only if the derivative switches sign as x increases through c. Okay. To test whether a function has a local extremum at a critical point c, you must determine the sign of f of x, the derivative of f of x, to the left and right of c. This is known as the first derivative test. Okay. Concavity and points of inflection. Let f be a function that is differentiable over an open interval I. If the derivative of x increasing over I, we say the function is concave up. If the derivative is decreasing over I, we say f is concave down. Concave up, concave up, concave down. If the double derivative is more than 0, so double derivative would be like the derivative of the derivative. This is, so like the derivative is the gradient. The double derivative is if the gradient is increasing or decreasing. It's a change in gradient. So gradient decreasing, decreasing, decreasing. Let's pick another one. The double derivative is decreasing, decreasing, decreasing. Then at this point, the gradient is increasing, increasing, increasing. So would be negative because it's decreasing. And then over here, would be more than 0. This is less than 0. This is more than 0. Okay. If f is continuous at a and f changes concavity at a, the point a, f of a, is an inflection point of f. This point would be an inflection point because the double derivative is changing. F, the derivative is 3x 3x squared 12x plus 9 6x minus 12. No? Yeah. So this is like a straight line, very steep. So or can just do this. Well, it's a very steep line. This is negative 12. So the double gradient is 0. Wait. So when is the double gradient 0? Two. If x is less than 2, then the double gradient is less than 0. It's more than 2, then the double gradient is positive. So the gradient keeps increasing. Concave down, concave up, decreasing, 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 and then the gradient is increasing. Second derivative test. The first derivative test provides an analytical tool for finding local extrema, but the second derivative can also be used to find local extrema values. Using the second derivative can sometimes be a simpler method than using the first. We know that if a continuous function has a local extrema, it must occur at a critical point. However, a function need not have a local extrema at a critical point. Here we examine the second derivative test can be used to determine whether a function has a local extremum at a critical point. Let f be a twice differentiable function such that the derivative at a is 0 and the double derivative is continuous over an open interval I containing a. Suppose the derivative of f at c is 0. Double derivative is continuous over an interval containing c. If the double derivative at c is more than 0, then f has a local minimum at c. Oh, I see. I got it. So if it's like this, the derivative is 0, but the gradient is increasing over time, so the double derivative would be more than 0. Then if it's a local maximum, the derivative would be 0. The gradient is increasing, but the gradient is decreasing, so the double derivative would be less than 0. More than 0. And it's like this, straight, straight, then it's inconclusive. Right? The derivative at -1 is less than 0. It's a negative, but over here is also negative, so this is not in local extrema. Find the inflection point. Inflection point is when the double derivative changes. Wait, let me go up. So what is the first derivative test? If the derivative changes sign from positive to negative, then it's a local maximum. If it changes sign from negative to positive, then it's a local minimum. If it has the same sign, then it's neither a local maximum or nor a local minimum. And the second derivative is, yeah, it was this. Basically, we are using double derivatives for the same thing. Inflection point is where the double derivative changes. So let's say 3 derivative 3 square double derivative 6. If it's 0, the derivative at 0 is 0, the double derivative at 0 is 0. Now the double derivative wait, hold on. One, and then the double derivative at -1, -6. So I can say that because of this equation, then 0 implies 0, x more than 0 implies. So this is an inflection point. This is true. Now, is it a local maxima? I know the answer is no, but audio, okay. So 1 is equal to 3, and then, oh, derivative, still 3. Because of this equation, we can determine this. So it's not a local maxima or minima. Next. Limits at infinity and asymptotes. How many chapters? This is taking forever to load. Chapter 4. Okay, maybe I should do this chapter and then end the stream. Limits at infinity. We begin by examining what it means for a function to have finite limit at infinity. Then we study the idea of a function with an infinite limit at infinity. Limits at infinity in horizontal asymptotes. Recall that limit of f of x is equal to L means f of x means arbitrarily close to L as long as x is sufficiently close to A. Okay. We extend this idea to limits at infinity. For example, consider the function f of x is equal to 2 plus 1 over x. As can be seen graphically and numerically, as the values of x gets larger, the values of f of x approach 2. We say that the limit as x approaches infinity of f of x is 2. We write it like that. Similarly, for x less than 0, as the values of positive x gets larger, the values of f of x approaches 2. We say the limit as x approaches negative infinity of f of x is 2. Okay, cos x plus 1. For each of the following functions, evaluate limit to infinity and negative infinity. Okay, hold on. So limit to infinity would be 5. because this just gets lesser and lesser. And the same for negative infinity. So limit right. This is 0, I think. Yeah, because x just gets a sine x is just repeating, but then x gets larger, so this will get smaller and smaller. So it would be like this. And then arctan. Let me graph that. Tan x. Hold on. If I choose degrees, what is this? Is this 90? Yeah. Whoops. Oops. Hold on. Wait. What is pi over 2? I think it's this. I think it's pi over 2 for the positive infinity and negative pi over 2 for the negative infinity. Identify where the vertical asymptotes are located. Okay. Negative 3 and 2. 2 and minus 1. 2 and 1. And 0. 0. And that's it is. 2, 5, 5. Yeah. Determine whether there is an asymptote at x is equal to a. Yes, there is an asymptote. 2, 5, 7. Okay, evaluate the limit. At x keeps increasing, like as x keeps increasing, the limit grows closer and closer to 0. So 2610, 269, as it goes to infinity. I think it's Hey, let me think about this. I think it's 4, but I might be wrong. I think both of them increase at the same rate, so I'm not sure. Um, wait. This is -4. Oh, yeah, it's going to the negative side. So what I was thinking, this -1 would be insignificant for like very large numbers. Right. If x is for like very large numbers, this would be the -1 would get insignificant. So it would be like this. Maybe. But then this, if this tends to infinity, this tends to negative infinity in the same rate, or very large numbers, they should cancel each other out. This would be -4. And you should be left with -1. Yeah, I guess I will end the stream here. Maybe I will learn Japanese or maybe a programming stream. I really want to learn C. So I don't know. Let's see.